A projector with the speed of light. Yes, the masked professor is back on the air. Return with us now to those thrilling days of, well, actually right now. All right, today we will be going into Chapter 8, which is about displays. All right, so all right, finally. All right, so when we say displays, that covers a lot of territory. They're defining displays as human-made artifacts designed to support the perception of relevant system variables and facilitate further processing of that information. Oy vey. So, some examples might be the speedometer in your car, the gauge on a machine, or fine print in a contract. Displays cover a lot of territory. Very often they're linked with a graphical user interface or GUI. Okay, well, what a concept. So, let me show you figure 8.1 on page 185. All right, so the idea behind a display is that we have a system that it is giving us information that is spreading out through some medium of display. We are getting that information to our senses, and we are going through the perception, situation awareness, and understanding. All right, so it's really not that difficult to understand what's going on with these displays. Being careful to switch back to computer, which, as y'all know, I'm very poor at remembering to do. So how do we classify our displays? Well, first of all, we could do it by the physical properties of the display, whether that's differences in physical implementation of the display device, or some other. When we create a display, we have to think about, are we going to use color versus monochrome? In other words, shades of gray. Visual versus an auditory modality. And what is the relative location of our display elements? If they're visual elements, obviously they have to be put where they will be perceived, where auditory modalities are going to allow a 360 apprehension. So physical properties is one way that we talk about displays. Another is the tasks that they are designed to support. the designer has to understand the nature of the task that is supported. Is it navigating? That could be a GPS in your car or on your phone. Is that a sign that has an arrow pointing saying laboratory that way? Are the displays used in controlling some process? Right? That is going to give us a different set of rules and requirements for the display. Is it to support decision making? We use displays sometimes to support decision analysis. So, or is our display for learning, such as the display you're seeing right now? Okay, so first we have to define the task. Defining the task is actually always the first step in human factors or any kind of engineering design. We need detailed information analysis. We have to know what information has to be presented. It can't be a speech where we start going, we hold these truths to be self-evident. You know the thing. No, we've got to know what the information is. All right, of course in human factors, we say that the properties of our human user are going to give us the best mapping between the display and the task. So no single display tool is suited for all tasks. Right? Having a sign that says restrooms is very useful. But having a sign saying don't turn this switch off at the nuclear power plant, it's not really going to help us much. So digital display is used for exact values that, but it won't show a change in the rate at which something is happening. All right, our best mapping between the physical form of the display and the task requirements, we get that by using our principles of perception and engineering and information processing. Oh, bloody hell. It's been a long day. So we have 13 principles of display design. They fall into 4 categories. Directly reflect our perceptual operations. They're related to our mental models. They relate to human attention. They relate to human memory. Okay, so those are the 4 categories. And now we have our 13 principles. First, of course, are the perceptual principles. Well, I say, of course, that's just the order they have them in this book. First of all, make the displays legible or audible if it's an auditory. Remember your guidance from chapters 4 and 5 on what is able to be seen and be heard, right? So we want to think in terms of the contrast, the visual angle that people can see, the illumination under which the display is going to be used, the noise that might be in the background, and masking, whether it's noise masking or clutter masking. The second of our perceptual principles: avoid our absolute judgment limits. So, if we are working with something that we're color coding, we want to remember not to go above having 7 colors. But on the other hand, if we're presenting auditory information, we want to make sure that our sounds are easily distinguishable one from the other. If an alarm goes off and everyone looks at each other and says, "What was that all about?" And then says, "Oh, don't worry about it, get back to work," that's no good for us at all. Our third principle is to use top-down processing. Our perceptions, we're going to get raw from the environment, but our interpretation is based on our experience, right? So top-down processing is based on knowledge and expectancy. Experience gives you that expectancy. If the signal is contrary to our experience, we need more input signals. All right, our fourth principle under perceptual principles is that of redundancy gain. We're going to get the information, interpret it more successfully if it's presented in more than one way. Alternative physical forms are going to be better. Tone and voice, voice and print, print and pictures, colors and shapes. One thing I would put in there is actual physical movement. I know that Cadillac and some other car companies have experimented with using a seat shaker or a steering wheel shaker to signal lane departure. So that is actually pretty good. I have also seen cars where you get lane departure warnings both visually and an alert signal. So those alternate forms mean one form might be degraded for whatever reason, but the other one has a chance of getting through. All right, and our fifth principle is that of discriminability, right? This goes back to discussion about absolute judgment limits. If we have too much stuff, too many different signals, whether it's different color coding, different sounds, we're going to get overwhelmed. So, similarity is going to cause confusion. So they're likely to be confused at our perception or in our working memory. Similarity depends on the ratio, not ration, of similar features to different features. So anytime that a confusion could be serious, we want to delete unnecessary similar features and highlight our dissimilar features. And I am going to I may have to go out a little bit. All right, there we go. All right, so if the light is amber, proceed with caution. All right, so that is an absolute judgment basis. Top-down processing, have a checklist. A should be on, B should be on, C should be on, D should be on. We can gain through redundancy, and the example there is the traffic light, right? Red is always at the top or the furthest left, and we know that red means stop, that yellow means caution, it's always, yellow is always in the middle, and green is always on the bottom or the far right. Right? So that way we have two different ways of signaling by the position of the light and the color. All right. When we talk about similarity, we can get confusion because of, we're looking at, these are two displays, but they're showing what looks like the same stuff. Well, maybe it's the same stuff, maybe it's not. In fact, in that last illustration, we might actually get confused about which one is mapping what part of the process or whatever we're thinking about. All right, so next up are our mental model principles. First is the principle of pictorial realism. Our picture of what we're controlling or we're monitoring should look like the variable it represents. If we're talking about a thermometer or a temperature gauge, that has high and low values, so the best way to represent it is vertically. Our multiple elements in our display should be configured the same way that they are in our environment, if we can. That may not be a realistic method of looking at things. Oh. The principle of the moving part. Our moving elements in the display should move spatially. And they should be compatible with our user's mental model of how the element actually works, moves in the system. Okay, well, Not too many there on the mental model principles. Principles based on attention. First of all, we have to minimize the information access cost, right? Because if we don't, we'll be into satisficing, and that may not be the best way to handle the situation that we're talking about. We want to keep our displays small so that there's not much scanning. That way we're minimizing the cost to access the information. But we have to keep in mind it has to be big enough to be seen. If it's too small, we may not be able to see it. It may not be legible. Next is our proximity compatibility principle. If we have two or more pieces of information and they're related to the same task, maybe we have to mentally integrate them to complete the task. If they're in separate places, we're going to have divided attention. And of course, as we've already established, divided attention, double plus ungood. So let's put those sources close together. Or we can link them with lines on our display. We can have common colors so that we can immediately see, oh wait, all the blue stuff is doing something strange. I better put all that information together. Put it into a pattern. All right, so here we have a figure on page 190 that shows us how we put things into a pattern. And you'll notice on the left are the close ideas versus on the right are the distant ideas, right? So we always want to put things together that go together. If we can. Sometimes that may not be possible. All right, so let me just make a note here. All right, but we don't want to put them close together if only one of them requires focused attention. The third principle is the principle of multiple resources. Divide that information across resources. If you have visual and audio going, you'll be able to comprehend both rather than two visual displays or two auditory things happening at the same time. Same thing if you could make part of it a physical situation. All right. Our memory principles, we want to replace our memory with visual information. In other words, we want knowledge in the world so that we don't have to keep that information in our working memory. So there can be, there are some suggested methods here. A visual echo of numbers, in other words, instead of hastily trying to memorize a telephone number, it pops up right there on the display. Checklists are very useful always. A simultaneous display is not as good necessarily as a sequential display of the information, right? You've got this, you've got this, you've got this going on. One thing we always have to remember, don't let it get too cluttered. Sometimes people want to show every damn thing that is happening now, has ever happened, and ever will be or. Not a good way from a human factors perspective. All right. Our second principle under memory is the principle of predictive aiding. Human beings in general are not good at prediction. That makes it a very difficult cognitive task. When we overload our mental resources, we are going to be reactive rather than proactive. And of course, for prediction, we want to be proactive. So the predictive displays are going to support our human performance. That removes the resource-demanding task and instead replaces it with a perceptual task. Okay, well, remember that till you die. Third, under memory principles, is the principle of consistency. We want to design displays to be consistent with other displays that are happening at the same time. Our color coding should always be consistent across displays. And our different displayed panels need to be organized so that they are reducing the information cost that the user is having. However, kind of a side note, use common sense when these principles conflict. And they will conflict from time to time. All right, so let's talk then about alerting displays. When it is critical to alert the operators or the users, the auditory channel is best. We have 3 levels of alerts. One is warnings. Warnings are the most critical category. We want salient auditory alerts with redundant visual signals. As I pointed out here in the classroom, the fire alarm does exactly that. It has not only a very raucous sound, but it also has a xenon flashing lights that get your attention. All right, our next level of alert is a caution. We signal that by something less salient. We might use a soft voice signal, and it's still helpful to use redundant visual signals. And then the lowest level of alert is an advisory. This one is usually mailed to your home. No, I'm kidding. Of course, that's not how it's done. But, for example, you may have noticed you buy certain products, and right on the box when you buy it, there's an advisory, caution, do not stick this up your nose, or, you know, some other thing that somebody has done, and they're trying to keep you from doing it. All right, so our next category of display are labels. These are displays. Generally, a label is static and doesn't change. They should unambiguously signal an identity or function. So they might be for a control, for a display that tells you what that display is showing, a piece of equipment, or an etc. Damn it, I hate it when they put an etc. in here. So much that I'm going to go ahead and take it out. That's how I feel. Labels represent knowledge in the world. They can be print or they can be icons. Now, sometimes if they're icons, you don't really understand if you cross cultures. For example, when we went to Poland with the ice show, they represented the male restroom as a triangle and the female as a circle. And I've noticed that starting to pop up more and more here in America now, but that did cause considerable confusion at first amongst our iShow cast members and staff. Oh, right, icons. So, our design criteria, first of all, the visibility and legibility of a display. Part of that is the stroke width of lines, and I still haven't had a chance to put together an experiment with signs, as I've wanted to do. The contrast, very often you see a display where the letters are light blue and the background is a slightly darker blue, and that can be impossible to read for older people because they start losing their blue seeing ability to a certain extent. We need them to be perceived even under the poorest conditions. I have had people tell me, oh, that's fine, I can see that sign fine from here. Things like an exit sign to leave the building. Well, can you see that exit sign if there's a fire and this room is full of smoke? That's the question. All right, so discriminability, of course, we highlight the differences. We eliminate redundancy between labels whenever we can. And we need to remember the principle of negation, which is that if you say no exit or not an exit, some people will read that as exit. Meaningfulness is very important in labels. Is this label going to trigger the appropriate translation in their head or not. Remember that you as a designer may think something is meaningful, but it may not be to everybody else. Of course, icons are good, particularly where we have multiple languages and or cultures. And icons are good for degraded conditions. When we think of the location of labels, we want them to be physically close to what they are mapping. And to be unambiguously associated with what they're mapping. All right, so monitoring, when we're monitoring, we may be viewing things that are potentially changing. It might be channel frequency, it might be speed, temperature, noise level, changing job status. No, that doesn't mean the display tells you you're fired, but that a job has gone from, all right, the job was held up, it was on a red, now it's changing to a yellow, and now it changes to green because we can go ahead again. Our monitor may need to be set at the beginning of a job or at intervals. They need to be watched until some value reaches a triggering action. Now, the difficulty with that is how long does it take for the value to get to the triggering action? 20 minutes is about the limit for intense, concentrated attention. Okay, something that needs to be tracked. So we have guidelines for monitoring. First of all, legibility. Funny how legibility always comes up. There's the contrast sensitivity. Can I see the print on the display against the background easily? If the monitoring display is digital, what is the print resolution and the character resolution? You don't want to be using a bunch of crazy fonts that are hard to read, and you want to make sure the print is large enough and easy enough to read that you can monitor. If we have analog or some kind of pointer display, we have to keep in mind the visual angle that the person can perceive and the contrast of that pointer. The scale on that analog display has to be legible, right? It does us no good to monitor the pointer if we can't read the numbers or whatever that are behind. And again, we always have to think of degraded viewing conditions. All right, so what about analog versus digital? When quantities are monitored continuously, we're talking about changing quantities. Analog, we want the principle of pictorial realism. That gives us an advantage in a continuously changing quantity monitoring situation. Analog displays are more easily read at a glance, right? Think about the difference between looking at a clock that has hands versus a digital clock. Our analog display value is going to be easier to estimate as the display is changing. And it's also easier to estimate the rate and direction of the change. So we're monitoring a display. We see a gauge that is going up. Is that good or is that bad? If it's coming down, is that good or is that bad? All right, digital displays have possible advantages because print resolution can be very good. Character resolution, we have to make sure that both the print resolution and the character resolution are good. They have an advantage if we have to have a precise reading, right? If we have to say 57.5 versus it's around 55 somewhere. A lot of times we want to use a digital display redundantly with our analog display. All right, so our analog form and direction, again, keep in mind the principle of pictorial realism. Scale needs to be in some form and move in a direction that is going to match up with the user's mental model. Things that are cyclic or a circular variable, the examples that they give are compass direction or a clock. Okay? Make that a circular form. Our linear quantities, where we have a high point and a low point, go ahead and use a linear scale. The best is to array it vertically, where high is up and low is down. Okay, and let me, there we go. All right, 196. Oh, too far. All right, so you see here at the far left a digital display, right? It just gives you the number 15. Here we have a moving pointer analog display. Right, so here, these are with the principle of pictorial realism. Our C is a moving scale analog display with a digital readout, right? So you've got the principle of redundancy there. And D is a very poor example because the highest number is at the bottom and the lowest number is at the top. Oh my God, what were they thinking? All right. Sometimes we have displays that are dynamic, right? In other words, we can see visible movement within the display. So we want to stick with the principle of the moving part. So that our displays move in the direction the user's mental model think it should move. So an increase in speed, we move upward on the moving element. Rightward or clockwise is also an acceptable alternative, right? But again, figure 8.7D is in violation and probably got written a ticket. No, wait, that doesn't make any sense. Okay, if we have a linear scale, it can't give us a large range of scale values in a small space. In that case, we might want to revert to a moving scale display, use a circular display, now, I have seen back in the day, there were cars where the speedometer was not the traditional analog circular display that we see now, where it would actually be a display and here's 0 and then it's moving out like this to show you the speed, right? But we'll get to other things later that tell you maybe we shouldn't do that. All right, hybrid scale, if we have high frequency changes, they're going to have a moving pointer on a stable scale. Where if our changes are not as frequent, we can gradually shift the scale quantities, right? So airplanes actually usually use an altimeter. In other words, how high is the airplane? Like that. It has a circular scale for 0 to 1,000, and then there's an inset digital part to tell you how many thousands of feet we're at. When we're thinking in terms of control, an upward direction or clockwise is expected when we increase. And that is true whether we're looking at a digital, a display, or we're talking about the actual control. You expect to move a knob clockwise to increase something, or a slider that goes up to increase. All right. One thing that we do at times is we want to make a, oh bloody hell, we want to make a predictive display. But some things are very sluggish. A large ship, you input a turn and it doesn't happen for a while. In a chemical plant, you want to increase temperature to speed up the reaction or decrease something, the feed of something, that is going to be delayed, right? So these are what we call high inertia systems. That slow change means our future state is more certain, but what we do to control is going to have an effect later, after a while. So our control is based on our user's prediction of the future state. So we want to have predictive displays that are helping us with monitoring and control. Our prediction isn't always correct, and the further into the future that we are predicting, the less correct we're going to be. So using a predictive display, you definitely want to remember number 7 here. And if you're designing a display that's going to predict, you might want to tell them what is the level of uncertainty at which you're operating. Right? It's that old statistics thing. Build in the alpha error. All right, well, what about when we're talking about multiple displays? A nuclear power plant can have 35 critical variables, all of them critical. So, our display layout, we have to be able to define what is the primary visual area, or PVA. Right, and we can do that in a number of ways. First of all, if we have a seated viewer, the forward view is going to be their primary visual area. For a vehicle user, whether we're talking a truck driver or an airplane pilot, the direction of view is going to be the highway or the runway. And we have to think in terms of frequency of use. If a display is frequently used, we want it right there adjacent to the PVA, that primary visual area. That helps us to minimize the travel time and the access cost. Okay, and of course, we have our famous illustration. Let's see if this whole illustration fits onto the screen. All right, so this is figure 8.8. It's a cockpit display, right? So you'll notice we have the airspeed, the attitude indicator, the altimeter, we have a turn and slip indicator, a directional indicator, and a vertical velocity indicator. Okay, so so the dashed line around here is showing us the position of the aircraft, where the solid line is the controls that are controlling the vertical aspect of the airplane. Now, the FAA actually goes ahead and specifies how this should be done in an aircraft. The importance of use are displays that give us important information have to be located where they will capture attention. If they're not in the primary visual area, we need an audio alert and guidance about where to look. We want to display things that are related or have to be used in a certain sequence. So if displays are related, they should be close together. The proximity compatibility principle. Okay. So we want consistency when we are putting this together, right? Our memory and attention are going to work better if it's always consistent where you look to find information. In fact, that was the one thing that that I was kind of surprised at in the Mini when BMW put that out. I had not ever seen a British Mini Cooper, but in the BMW, the speedometer was in the center of the console and not where you would look through the steering wheel to see it like you do in most cars. All right, so we want the same items always positioned in the same spatial location, so that we have a memory of where things are, and that memory is going to guide the selective attention that we bring to the task. Now, consistency can be in conflict with our frequency of use, our relatedness, and if we have phase-related operations. For example, to start up the process at a chemical plant requires a whole bunch of different actions than to monitor that while it's making the chemicals, or for that matter, to what you do to shut it down. So, the variables in one phase are going to be different from another phase. So again, our information that's important for startup or shutdown is different from routine operation many times. Information for an emergency is likely to be wildly different than our routine operation. Now, one thing is that we can use what are called soft or computer-driven displays, and they can have a more flexible format. For example, we're going to start up our chemical plant, so we pull up the startup menu, right? Then as it's transitioning, it pulls up the routine operation menu. Our guidelines here are we want salient visible signals what configuration we're in. We want consistency across our different formats when that's possible. And keep it as simple as possible. Again, engineers always want to add more bells and whistles because we think it's cool to know how to do everything in the universe. Fight this tendency. All right. So now we're going to talk about organized grouping. We cluster displays, of course, that have relatedness. That guides our attention to groups of displays. And of course, oh, thank dog I have been talking with the camera on all this time, and you've been looking at paper. Well, damn it, it's too late. I'm not going back now. We're getting close to the end of the class. All right, but this is figure 8.9 on page 201. You'll notice that here we have good clustering where things are together, whereas on the right we have poor clustering. I will have this video posted on Moodle so that you can watch it, but when you get to the part where I forget to switch the camera, switch to the human factors outline, which will also be posted. Boy, is my face red. But luckily, I don't think you can see me very clearly here. All right, so we want to organize and group our displays. With a stimulus response kind of thing, we will also want our compatible displays to be close to our controls. I know that my human factors teacher always used to say, compatibility is the key to human factors. We want clutter avoidance, but we still want the minimum visual angle between displays, right? If something is out of sight, it's out of mind, as the old cliche reminds us. All right, so next we're going to discuss heads-up displays and display overlay. A heads-up display, or HUD, we superimpose information on top of the primary visual area. Military aircraft often have this kind of arrangement. And I know that Cadillac offered some cars that had heads-up display, particularly with infrared vision for night driving. All right, so the advantages are our driver or our pilot spends most of their time looking out where we want them to be looking. That way they are looking at the things in the far domain, the stuff outside in the environment, and the stuff in the near domain, the instrumentation, at the same time. We want to present our imagery with direct spatial counterparts in the far domain. When our imagery overlays its counterpart in the real world, we call that being conformal. Heads-up displays are projected by what we call collimated imagery. Oh, bloody hell. So, in other words, it appears to be at optical infinity, which makes it easy because it's taking that near domain information and projecting it like it's far domain. There's a cost if it violates excessive clutter. If you have too many things on the heads-up display, then it's going to start to get in the way of seeing the actual world. The benefits of heads-up display seem to outweigh the costs, though. So we've got that going for us. All right, very similar to the heads-up display is the head-mounted display. When it's head-mounted, it could be like a visor or a face shield, or it could be a helmet-mounted display. That way, you're not stuck with, okay, I can only see this stuff if I'm looking forward. With a head-mounted display, what you're monitoring is consistently displayed as you look right or left. So our user can view the imagery across a wider range by doing that. It minimizes the information cost and is hands-free. A head-mounted display can be either monocular or binocular. In other words, it might be something that only one eye is seeing versus something that both eyes are seeing. So with monocular, it can be opaque or it can be transparent. There is less clutter than a heads-up display, although that's really an issue of design. It's not built into the process. If we have different images to our two eyes, that can be a problem. Some people can cope with that easily, others not so much. So you can get binocular rivalry. One eye is fighting the other for what the brain is going to see, or binocular suppression. Again, the eyes are competing for what the brain is going to see. So, now there's also a problem of what are we showing on our head-mounted display. If we're trying to show conformal images, in other words, enhance things that we're seeing ordinarily, they might not be updating fast enough to keep up with head movement. So that can lead to the image being distorted and getting motion sickness. So the evidence seems to be mixed about whether a handheld display or a head-mounted display is better. There can be legibility issues on a small handheld display. the conformal imagery on a head-mounted display can integrate near and far domain information, but if that imagery isn't updated fast enough, that value is diminished. It's also diminished if there's a cluttered display or too much visual information. All right, so configural displays are, we have multiple displays of single variables. Sometimes arrayed, or maybe arrayed would be actually better, so that the properties that are relevant to our task are going to be seen more easily by glancing at a group of things or a couple of things at the same time. All right, here we go. And that's page 206. And this is page 207. All right, so I'm going to switch to camera and show you figure 811. Okay, and these are two different kinds of configural displays. This top one is for a patient that is on a respirator. Very timely right now. Right, so we see the volume that is going through the respirator by the depth of this rectangle, the amount the patient is breathing, and what is the rate between those. The second is a radar chart of, what have we got there? 7 different variables, right? As long as you're within this solid line here, you're all right. But on the other hand, if the variables are reading outside that solid line, we got big problems, boss. Okay, so configural displays are configured to create attentional glue. In other words, the proximity compatibility principle. All right, so, for example, this display has been designed so that if everything is running normally, there's a line right across all these gauges, right? But you can see right now, the FW press, some kind of pressure, is too low, and there's an alarm light on as a result. A similar situation occurred during the Vietnam War. During Vietnam, was really our first experiment with using helicopters really extensively, not just for medical evacuation or putting spies behind the enemy's lines, but actually using them to transport our troops for blocking or other maneuvering. So they were churning out helicopter pilots by the long time. They were just training these guys up and sending them through as fast as possible. But, as you can imagine, the problem was these guys were not as well trained as they should have been necessarily. And, of course, in the helicopters, there were a lot of gauges that had to be monitored continuously. So, somebody finally had the bright idea, hey, we're going to turn all the gauges so that when you're in normal operating parameters, all your pointers are pointing up. If you have something that departs from being up, you know that that needs attention. And that was kind of a brilliant idea on the part of somebody who God only knows who that was. So, anyway, I am going to stop here and pick up with supervisory displays next time. Please stay safe, stay healthy. We're going to get over this when the fields are white with daisies. Well, sooner than that, really. Anyway, have fun now.